All right, quiz 5 solutions for Math 243. So here's our quiz on hypothesis testing. So read through the problem, let's just go through it together. A study found that the average number of words spoken among all Americans, here's this population average right here, is 16,125. All right, fine. That's mu naught. That'll be kind of the baseline average that I'm comparing things with. And it gives me this population standard deviation of 5,000. So sigma is 5,000. So if I put a comma there, I can put a comma there. And then we get into the sample here, a random sample of 100 7-year-olds. So this is my sample size, n is 100. I calculate the average number of words spoken to be 17,000. That sounds like X bar. And what I'm supposed to do is test the claim that 7-year-olds speak a different number of words than the average American, assuming a 95% level of confidence. That tells me that alpha is 5%, or 0.05 if you want to write that as a decimal, by following the steps below. So first, null and alternative hypotheses. So the idea with your null and alternative hypotheses is they're both going to compare mu, which would be the population average number of words spoken by all 7-year-olds. So not the population average number of words for all Americans, but just of 7-year-olds, not the sample of 7-year-olds, the population. You're comparing mu and mu naught, the population average for all Americans, the 16,125. And you do that for both mu and mu naught. For your null hypothesis, you probably always put an equal sign in between here. For your alternative hypothesis, it could be a less than sign, a greater than sign, or a does not equal sign. But because the claim says a different number of words, that's why we have this does not equal sign. And this is a two-tailed test because we put a does not equal sign. So there's our null and alternative hypotheses. And you don't have to write that it's a two-tailed test. This will get you full credit, that box right there. State and justify the shape center spread of the sampling distribution. Sure. Well, the shape's going to end up being approximately normal, or normal, either way is fine. And I know that because otherwise I wouldn't even be able to do the problem. I wouldn't be able to do my hypothesis test in the future steps. But really the reason it's approximately normal is this thing called the central limit theorem. It says that even if you don't know the shape of the parent distribution, which is, I think, the case in this problem, if n is large enough, greater than or equal to 30 is the criteria we use in our class, then the shape of the sampling distribution is approximately normal. The center, the value is just the value of mu naught given to you in the problem, in this case 16,125. And the spread is sigma divided by the square root of n. Both things given to you in the problem, in this case 5,000 divided by the square root of 100. In this case, that works out really nice. That's just the number 500. You can calculate it if you want. I don't need you to. Classical method picture, sure. So you want to draw something that's approximately normal because we're drawing the sampling distribution. And right above, I just said that it was approximately normal. I'll put 0 in the middle to represent 16,125 words. This is the z-score representing the center. And then since this is a two-tailed test, because I put a does not equal sign there, alpha has to appear kind of split up between the left tail and the right tail. So 5% is the total area, 2.5% is on this side, and 2.5% is on this side. And what I didn't need to do is figure out what z-scores correspond with the points that separate the outer kind of 5% from the inner 95%. And you do that with the inverse norm function on your calculator. So that lives under the distribution function, second and then variables. And if you find one of them, maybe we'll find this one first. You can use symmetry to get the other one. So the area to the left of this point is 0.025. And then the center and the spread are 0 and 1. You can put comma 0, comma 1. If it turns out if you leave them out, it just assumes comma 0, comma 1. At any rate, this is negative 1.96 over on this side, which means this is positive 1.96 on this side. And just for the sake of showing my work, I'll write that I got this by doing inverse norm, 0.025, 0, and 1. And that gave me that number. And now what I want to do is find my test statistic. And if my test statistic's in the rejection region, what I shaded, then I'm going to reject my null hypothesis. Get your test statistic out of the z-test function. Stat, then tests. The first thing listed said z-test. And you put in all the statistics given to you in the problem. So mu naught in this problem was 16,125. Sigma in this problem was 5,000. X bar in this problem was 17,000. And N in this problem was 100. And my claim was that mu does not equal mu naught. That's what I put right here. And I can go down to calculate, and it'll tell me my test statistic. And my test statistic is 1.75. So I don't know, my picture, maybe that's like roughly here. Z equals 1.75. Note that it's not in the rejection region because it's between 0 and 1.96. I wouldn't have been able to tell if it was in the rejection region if I didn't have this critical value. I believe that that's everything. There's alpha, there is the critical values, and there's my test statistic. So now I state my conclusion. So I can say because my test statistic, which in this case was 1.75, does not fall in the rejection region, well, what that means is there's not sufficient evidence to reject the null hypothesis. And if there's not enough evidence to reject the null hypothesis, then you cannot say that the claim is true. So I cannot conclude that, let's see, the original claim was that 7-year-olds speak a different number of words. So I can't conclude that they do that. 7-year-olds, sure, speak a different amount of words than everybody else. I guess that's implied. Something like that. 3 things. Why you're doing what you're doing, what that means for the null, what that means in the context of this problem. All right, then question 2 here is pretty similar to question 1. We use all the same data, so this paragraph is still applicable. The only thing that changes is instead of testing the claim that 7-year-olds speak a different number of words, we're going to test the claim that 7-year-olds speak more words than average, assuming a 95% level of certainty following these steps. So what changes here is my alternative hypothesis. My null hypothesis is identical. It's still that mu equals mu naught, and mu naught is still 16,125. But my alternative hypothesis, instead of being mu does not equal mu naught, is mu is greater than mu naught, which makes this a right-tailed test. Shape, center, spread, that's the exact same as it was above, same as 1b, sure. Be a little lazy there. And now I draw the picture. But when I'm drawing the p-value picture, it's going to look a little bit different. I mean, it always looks different because it's the p-value picture, but it's going to look especially different because it's a right-tailed test instead of a two-tailed test. I guess that's good enough. Still throwing 0 in the middle to represent the center, which is this 16,125 that I listed up here. But now I don't need a rejection region and a critical value. I can go straight to my calculator, stat tests, z-test, and then put in all this information. My claim is that mu is greater than mu naught. That's what I wrote up here. And then either calculate or draw. I typically do draw when I'm doing the p-value method, so I let it draw the picture for me. You'll note that it shades over here on the right. Makes sense, it's a right-tailed test. Shades to the right of my test statistic, which is 1.75 in this case. And the amount it shades is what's called the p-value, which in this case is 4.01%. So there's my p-value picture, and with that information I can state my conclusion. I want to compare my p-value to alpha, which is 5% still. So I could say something like, because, sure, my p-value, which in this case was 4.01%, is less than alpha, which was 5%. There is sufficient evidence to reject the null hypothesis. So I can conclude that, 7-year-olds speak more? Sure. 7-year-olds speak more than average. Something like that. Looking for the 3 things. Why you're doing what you're doing, what that means in terms of the null, and then what that means in the context of this problem. That's all I got.